In this lecture, we're going to learn how to solve polynomial inequality. So this is section 3.6. So why don't we start off with the definition of a polynomial inequality? So we've been used to solving equations, whether it's a quadratic equation, linear equation. Now we're going to solve these polynomial inequalities. So rather than have an equal sign, we're going to have one of the following inequalities in the expression, either less than, greater than, less than or equal to, or greater than or equal to. And the standard form of a polynomial inequality is either the polynomial is less than 0. So when we're in standard form, we set f of x, which is the polynomial. We're either going to solve for the polynomial being less than 0. And other possibilities, we want to solve greater than 0. We might want to solve for all values of x for which the polynomial is less than or equal to 0. Or we may be interested in solving for when the polynomial is greater than or equal to 0. So the first thing we want to do is make sure the inequality is in the form either f of x is less than 0 or f of x is greater than 0. Then what we're going to do for a moment is solve the equation f of x is equal to 0. The reason we're going to do this is because we're going to be able to obtain boundary points. And boundary points, once we plot them on a number line, they're going to divide the number line into intervals. And then what we could do is in each interval, we can pick a test value. And then we could evaluate f at that value and determine if the function is positive or negative. And then we can decide where our solution set is. So I know that sounds like a lot, but once we do an example, you'll see and you'll start to get the hang of it. And I think it's nice when we use a table. So let's just get into it. Let's just solve a couple of these because that's really all we're doing in this section. And you have all the tools already to be able to solve this because I taught you guys how to solve quadratic equations. And we're aware of how to graph a solution set on a number line and write it in interval notation. So if we kind of put all those things together that we've learned already, this is not so bad. So what I did was, you can see here, I created a table at the bottom, and I think it's going to be helpful to us. You don't have to put your work in a table. You can really just put it on, scratch paper right underneath. It's up to you. I just think this is an organized way of doing it, so you'll see what I mean. So for example 1, we want to solve the following polynomial. So we want to solve x squared minus 5x plus 4 greater than 0. So what we're trying to figure out is, for what values of x is this expression, x squared minus 5x plus 4, greater than 0? So what we have to do is, because there's going to be more than one solution, more than one value of x. So we're going to have to represent it using interval notation. And I also want to put it on the number line as well, the visual representation, and then it kind of ties it all together. So what we're going to do in order to get these boundaries, so remember up here I was saying we're going to get these boundary points. So what we do first is, let's just treat this statement here as an equation. So what I mean by that is, first let's solve x squared minus 5x plus 4 is equal to 0. And you guys know how to solve this. This is a quadratic in standard form, right? So if we're able to factor this, we could set each factor equal to 0, right? And solve. So in order to factor x squared minus 5x plus 4, we're going to have x minus 1 times x minus 4, because negative 1 times negative 4 is positive 4, and negative 1 plus negative 4 is negative 5, which is our b, right? So when we set each one of these factors equal to 0, so we're going to have x minus 1 is equal to 0, or we're going to have x minus 4 is equal to 0. So when we solve both of these equations, we're going to get either x equals 1 or x equals 4. Those are my boundary points. So what we're going to do is, because this is when the equation is equal to 4. But remember, what we're really trying to solve for is when is the polynomial expression greater than 0, not equal to 0. So 1 and 4 is when my function is equal to 0. But those are going to be like my boundary points. And it's going to let me test and see where the function is going to be greater than 0, which is really what we're solving for, right? So let's plot x equals 1. Now, 1 and 4 are not part of our solution set. And the reason is this is strict. Whatever x squared minus 5x plus 4 is, it has to be strictly greater than 0. Notice there's no little equal sign underneath. At x equals 1 and x equals 4, if I were to plug into this expression, we're going to get 0. And 0 is not greater than 0, right? So we're going to put open circles on 1 and 4. But those are my boundary points. So you see how putting the 1 and the 4 on, placing them on the number line or identifying them on the number line just broke this number line into 3 different sections. So what we're going to do is just on top, what interval represents this leftmost section, right? So it's going to be negative infinity to 1, right? But not including 1. And then this middle section right here is going to go from 1 to 4, but not including 1 and 4. And then this section right here to the right of 4 is going to be 4 to infinity. So what we're going to do is we're going to pick a test value or a test point within each interval and substitute it into our polynomial f and see if we get a positive or a negative value, and then we can make a conclusion. So let's list the intervals here in my first column. We could do one at a time. So let's do negative infinity to 1. So let's pick a number that falls in this interval. I'm going to pick 0 because 0 is always a nice number, but you could have picked anything, -1, -2, -6.3, whatever number's in this interval. So I'm going to test 0. So when I substitute x equals 0 into my polynomial function, I'm going to get f of 0 equals 0 squared minus 5 times 0 plus 4. And that's 4, right? Which is positive. 4 is a positive number. So my conclusion, so what's going to be true is any number that I pick from negative infinity to 1, I'm always going to get a positive number when I plug it in. So we can conclude that my function or the value of my polynomial expression is positive, or we would write that saying greater than 0, right? For all values of x in the interval negative infinity to 1. And my pen is glitching, so hold on a second. Okay, so for all x in the interval negative infinity to 1. So now let's pick a test value in my second interval. My second interval now goes from 1 to 4. So not including 1 and 4, right? So let's pick something in between. Let's do 2. So what if x was equal to 2? So the value of my function at 2 would be 2 squared minus 5 times 2 plus 4. So all I'm doing is plugging 2 into, I'm substituting it into my function. So we're going to get 2 squared is 4 minus 10, which is going to be -6, plus 4 is going to be -2. So we end up getting a negative answer. So any number that we pick within this interval from 1 to 4 and substitute it into f is going to give us a negative number. So our conclusion is that f of x is less than 0 or negative for all values of x in this interval from 1 to 4. And then let's do the last interval. So my last interval goes from 4 to infinity, not including 4. So let's pick a number in this interval. Let's choose 5. And again, you could pick any number you want in that interval. So f of 5 is going to be equal to 5 squared minus 5 times 5 plus 4. So 5 squared is 25 minus 5 times 5, which is also 25, right? So 25 minus 25 is 0, and then we're going to get 4, right? Plus 4. So that's going to be positive. So f of x is positive for all values of x in the interval 4 to infinity. And that's what we're trying to solve for, right? When is this polynomial, we'll go back to the original, greater than 0, right? When is the value of that polynomial positive or greater than 0? Well, that happens over 2 intervals, right? The interval from negative infinity to 1 and then 4 to infinity. So that's going to be my solution set. So if I graph these two solution sets, I'm going to shade everything in the interval from -1 to 1, and then I'm going to shade everything in the interval from 4 to infinity. So that's how my solution set would look on the number line. And then I also want to put my answer in interval notation. So my solution set in interval notation is going to be negative infinity to 1 union 4 to infinity. So in other words, if I were to pick any value of x in those two intervals and plug it into my original polynomial inequality, it's going to make a true statement. So let's try another one. Let's look at the next one. So let's solve x squared minus 4x plus 3 is less than 0. So first, let's set the polynomial expression x squared minus 4x plus 3 equal to 0, and let's solve that equation. So let's factor the polynomial. So two numbers that multiply to 3 add to -4, so that's going to be -3 and -1. And now set them each equal to 0, so we're going to get x minus 3 equals 0, or x minus 1 equals 0. So we're going to get x equals 3 or x equals 1. So those are going to be my boundary points. But 3 and 1, when I go to plug them back into my polynomial expression, is going to give me 0. And 0 is not strictly less than 0, right? I don't have a little equal sign here. So 3 and 1 are not part of the solution set. So I'm going to put an open circle on 3 and an open circle on 1 for that reason. So now this is going to divide my number line into 3 intervals. So from here is going to be negative infinity to 1. This interval now between 1 and 3 is going to be from 1 to 3. And then the interval to the right of 3 is going to be 3 to infinity. But we're not including 1 and 3 in any of these intervals because this is a strict inequality. So now let's get some test values within each interval. So my first interval goes from negative infinity to 1. I'm going to pick 0. 0 falls in that interval, and 0 is a nice number to choose. When we substitute, we're going to get f of 0 equals 0 squared minus 4 times 0 plus 3, which is 3. And that's a positive number. So what we can conclude is that f of x is positive or greater than 0 for all values of x in this interval from negative infinity to 1. So now let's look at the interval from 1 to 3. Let's pick a test point. I'm going to pick 2. Falls right in the middle. So f of 2 is going to be 2 squared minus 4 times 2 plus 3. So that's going to be 2 squared is 4. 4 minus 4 times 2, so that's 4 minus 8, which is negative 4. And then plus 3 is going to be negative 1. So we're getting a negative answer. So what we can conclude is that f of x is negative or less than 0 for all x in the interval from 1 to 3. And my pen is not working. Hold on a sec. Okay, so f of x is negative or less than 0 for all x in this interval from 1 to 3. And then we'll pick one more test value in my last interval from 3 to infinity. So let's pick, I'm just going to pick x equals 4. So substitute 4 into my polynomial expression. So we're going to get 4 squared minus 4 times 4 plus 3. So 4 squared is 16. And then 16 minus 4 times 4 is 16 minus 16, which is 0. And then we're going to get positive 3. So that's positive. So we can say that f of x is greater than 0 for all values of x in the interval from 3 to infinity. So this is when you have to go back to the original polynomial inequality and think about, all right, what are we solving for? We're trying to figure out the intervals or interval when x squared minus 4x plus 3 is less than 0. Well, we get answers that are less than 0 or negative when we pick numbers in that middle interval, right? From 1 to 3. So there's one interval, and that's going to be the interval from 1 to 3, where the values of my polynomial function are going to be negative or less than 0. So my solution set in interval notation is going to be 1 to 3. And this is what it would look like on a number line, the shaded area between 1 and 3. We'll do one more. And you know what? Let's do this. Let's change, not really change, let's just add a little equal sign underneath this inequality. So let's solve x squared plus x minus 6 is greater than or equal to 0, because I want to do one that includes equal to, because the steps are the same, but I just want you to see how it's going to be a little bit different when we set up the number line and write our solution set. That's all. So I want everybody to change this inequality to greater than or equal to. So just put a little equal sign underneath, and that's what we're going to solve. All right, so first, let's solve x squared plus x minus 6 is equal to 0 so we could get our boundary points. So let's try and factor x squared plus x minus 6. So two numbers that multiply to negative 6, but are going to add to positive 1. So that's going to be a positive 3 and a negative 2. So let's set each factor equal to 0. So x plus 3 is equal to 0, or x minus 2 is equal to 0. So we're going to get x equals negative 3 or x equals positive 2. So when I plug in negative 3 and 2 into my polynomial expression, we get 0. And 0 is greater than or equal to 0. So negative 3 and 2 are going to be part of our solution set. So now, because it's greater than or equal to, I'm going to put closed circles on the -3 and 2, my boundary points. So this interval on the left is -infinity to -3, but now I'm going to use a closed bracket because 3 is included. And then the middle interval now is going to go from -3 to 2. And then that last interval is going to go from 2 to infinity. So let's list our intervals, pick test value, substitute, and come to a conclusion. So my first interval goes from -infinity to -3. So let's pick a number within that interval. So I'm going to pick -4. Substitute it into f. So we're going to get f of -4, which is going to be -4 squared plus -4 minus 6. So we're going to get -4 squared is 16. 16 minus 4 is 12. And then 12 minus 6 is 6. So we're getting a positive value. So my conclusion is that f of x is positive or greater than 0 for all values of x in this interval from -infinity to -3. Now let's look at my next interval. So my next interval is -3 to 2. I'm going to pick 0 because, like I said, 0 is a nice number to plug in. So f of 0 is going to be equal to 0 squared plus 0 minus 6, which is going to equal -6. And that's a negative value. So we can conclude that f of x is negative or less than 0 for all values of x in this interval from -3 to 2. And now let's look at our last interval from 2 to infinity. I'm going to pick 3. So if x is equal to 3, let's find f of 3. So we're going to get 3 squared plus 3 minus 6. So that's going to be 9 plus 3 is 12. 12 minus 6 is 6, which is positive. So f of x is positive for all values of x in the interval from 2 to infinity. And we're looking to solve where my polynomial is greater than, greater than or equal to 0. And that would be in my first interval and my last interval, right? Because we're getting values that are positive or greater than or equal to 0. So my solution set on the number line is going to be everything shaded to the left of -3, and then everything shaded to the right of +2. And in interval notation, my solution is going to be -infinity to -3 union 2 to infinity. And that wraps up section 3.6. So 3.6 is just that one objective. So being able to solve polynomial inequalities. And the key is set the polynomial equal to 0 in order to figure out what your test boundaries are. And then once you have your test boundaries, you can divide the number line into intervals. And then for each interval, pick a test value, substitute it into the polynomial, and see if your result is positive or negative. And then you could decide which intervals contain the solutions to that particular inequality.